Hello everybody. Welcome to the Stats for the Masses webinar. Today it is Back to Basics 3, P-Values and Effect Sizes. My name is Elaine Eisenbeis. I'm the owner and principal statistician here at Omega Statistics. We did have a large number of registrants for this presentation, and I see a few of you are re-attending, so thank you for taking the time to join us live. Today I'm going to present a very brief overview of current controversies in the p-value approach to hypothesis testing. In our Back to Basics webinars, I presented scientific method, hypothesis testing. That's what we've been covering the last 2 webinars. But today I want to present a brief overview of the current controversies. I'm going to show you a bit more about how to think like a statistician when it comes to problem solving. I'll also provide some real-world examples of how the p-value approach falls short, especially with big data. Big data is the big buzzword, so I want to show how it kind of falls apart with that. Today's just an overview, but I hope that the information you receive today will give you some ideas and guidance on the use of statistics in your world. As I say in all of our webinars, use what you learned today, apply it in a holistic way. As a researcher, it's important not only to get the correct numbers and those p-values, but to look at the big picture of the study and use the numbers to inform your research. This presentation is probably going to last about 40 or 45 minutes, and then we'll take some time at the end of the presentation to answer some questions from our audience. I have currently muted the line so only my voice can be heard. But our board operator today is Rod Eisenbeis of Silverado Creek Studios. We have him to thank for helping to get our recordings in top shape before delivery to our viewers. If you call Omega Statistics also, he's the voice on the hold and away messages. The local radio station refers to him as Mr. Golden Honey Voice, and you will hear why if you stick around for the Q&A. Rod's going to be monitoring the chat board while I present the webinar. So feel free to type any questions you have on the chat board, and Rod will choose some to ask me at the end of the presentation. And yes, we do have the same last name. He's my husband. So thank you, Rod. If you have any technical issues, I often find that just logging out and back into the webinar clears up just about everything. So when in doubt, reboot. So let's go ahead and get started through our slides. And before I begin, I always like to take a minute to tell you about Omega Statistics and Stats for the Masses webinars and newsletters. Statistics can be a difficult subject, even for seasoned researchers. Often textbooks, classes, training programs, they can make things a little more confusing. And my goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate about statistical concepts in layman's terms whenever possible. Sometimes that's not easy, but I try to do my best so that everyone can see the elegance and usefulness of statistics. Our next webinar in the Back to Basics series is scheduled for July 20th, and I'll show you a little bit more on that at the end of the presentation. It is hands down our most popular webinar. It's the power analysis a priori techniques. If you want to know more about how to tie together what you've learned to figure a sample size for your study, then you should sign up for that one. Invitations will be delivered in the next week or so, but you can go right now onto our website at the Omega Statistics website and sign up. The webinars are always free and recorded, so if you can't make it to the live meeting, you can view the webinar later at your convenience. Here's some things that we do at Omega Statistics. We are a private practice. We do assist with medical and clinical research, all phases of clinical trials, dissertation assistance. We do help with the methods and results chapters, everywhere from just an analysis, if you only need that, to a full service where we write everything up, unlimited consulting, all different levels of service. Dissertation and clinical trials are probably the best things we do, but we do also do exploratory design and predictive modeling. We design surveys. We take projects on of all sizes, individual researchers, small businesses, startups, large corporations, and our motto is to provide elegant solutions effectively applied. Today in our webinar, we're going to cover a few things. We'll do a brief review of the scientific method, hypothesis testing, and p-values. We covered these in the first 2 webinars of our series, so we'll do a little refresher on those. And then we'll learn about what p-values can and cannot do. We're going to look at some problems encountered when using only a p-value to drive your study and your decisions. We will also have a little introduction to effect sizes. We will talk more about effect sizes in the next webinar too with the power analysis. They're very important for that. We will talk today about why an effect size is important, and I'm going to give just basically a slide with a listing of some other techniques that you can research for yourself. We won't have time to go over them today, but I always say Google's our friend, so You know, it's great. It's like a library right in your computer. So here we are with the statistics and the scientific method. Statistics is the keeper of the scientific method. We help all the researchers to make sure that their studies are robust, that they're valid, that they're reliable. That's up to us to make sure everything is in order. We use theory and tools of statistics to perform our studies according to the scientific method via hypothesis testing. And here are the 5 steps. First, you formulate your research questions and your hypotheses. Then you specify your statistical hypotheses, choice of an appropriate test statistic. Am I going to use a t-test? Am I going to use a regression? What am I going to use to test this? We're going to compute the probability, which is the p-value. And then we're going to determine if the results are significant according to whatever level of significance that we did set. And then we're going to properly state the conclusions and make inferences based on the test results. So as you can see, the basic scientific method approach really relies heavily on that p-value. The scientific method is a circular process. As you can see, we go round and round because we never prove anything. It's always guessing, we're always guessing, we're always trying, pull more samples. Often you will observe something and you'll kind of see some patterns. You'll form your hypotheses and maybe come up with a theory at the end. And that's inductive, that's bottom up. There's also deductive, where you start with your theory, then you make some hypothesis to test that theory, then you observe your data, and then you confirm whether or not your hypothesis is supported. And that's the top down. And this is usually for the dissertation kind of client and such, when you kind of have your theory to begin with. Here you have your observation to begin with, but they do tie together and they just go around in circles. Theory. Typical use of the word theory implies a belief based strictly on observation and the personal experiences of an observer, like a hunch. The sun's been rising every morning all my life, so it's going to rise again tomorrow. However, scientists use a theory as a conceptual framework to explain not only an observation of the sun rising every morning, which is basically just a fact, it does, but also the mechanisms behind that observation. In essence, the theory of gravity not only explains why the sun rises each morning, but also the path of the planets around the sun, tidal motion, projectile movement. So there's a lot of things involved in that theory. In everyday usage, a hypothesis is a guess that's not measured or confirmed. I hypothesize my new rooster is going to crow in the morning when the sun rises, okay? But to a scientist, a hypothesis is a working assumption. Typically, a scientist devises a hypothesis and then see if it holds water by testing it against data or information they collect from an observation or maybe even from previous research. If the test confirms the scientist's hypothesis does hold water, then the scientist declares his hypothesis to be a theory. And usually that's not right after one test. That's usually after testing and testing and testing. And that's why I put the note here. Usually it takes more than one hypothesis test and confirmation to arrive at a generally accepted theory. And this is because the scientific method must allow for reproducibility and falsifiability of a study's finding. And we discussed this in a little bit more detail in our second Back to Basics, if you want to go back and look at that. But here they are again. 2 very important aspects of the scientific method are the reproducibility. And you need to be able to give enough information so that it can be reproduced. It can't be something that you can only look at one time and then it disappears. So subsequent research must be able to collect the same type of data and perform the same set of processes as the original. Falsifiability, this is inherent in the scientific method. I always say we never prove anything. We might support things, but we never prove anything. So making use of the reproducibility is the opportunity for the reproduced studies to negate something that another researcher found. So maybe my study found, oh yes, there is something going on here. My p-value was significant, but another researcher could come along, pull another set of data in the exact same way even, and come up with a different conclusion. Maybe they didn't have a significant study. So we never prove anything. Further study could prove us wrong, and to quote Albert Einstein, no amount of experimentation can ever prove me right, and a single experiment can prove me wrong. So we have to remember it's all just guesstimates, right? Statisticians are adept at being educated guessers. If we knew the truth, you wouldn't need me. If we knew the truth, we wouldn't have to guess at it. We wouldn't have to do all this work. The scientific method helps us to make the best guesses possible with the information we collect. Frequentist statisticians who make use of the scientific method assume There's nothing that we know beforehand of the outcomes or how the phenomena works, such that the data must be collected and evaluated from information collected via a representative sample. And that's also usually a random sample. In many studies, we don't even pull a random sample. We can randomize into groups and such, and I think I covered that a little bit in one of the past webinars, but we just assume we know nothing. We're just going to go out and pull a sample and let that tell us everything about what we're studying for that study. Most researchers will use these frequentist methods. It's the way it's always been done. There are other types of statistics. There's Bayesian statistics and such, and they do have something where they assume they know a little bit about what's going on before they run their test. They have a priori hypotheses and such, but not in frequentist, not in the typical. So we have to use that p-value. It's very important. P-value is short for probability value. It's the probability of getting the observed or more extreme results given that that null hypothesis is true. And remember, the null hypothesis, the one that says there is no relationship, there is no difference in my groups, no correlation between my variables, there's nothing going on here. That's the null. And the p-value is the number used to answer that question. How rare would this finding be if truly there was nothing going on? It's a probability. So of course, if it's rare, you would want that probability to be low. So small p-values are what we would like to see. The smaller, the better. Many studies use a 95% level of significance, and this means that we're allowing ourselves to be incorrect in our guesstimates and conclusions that there is indeed something going on here 5% of the time. So, and here's a little math. It's 100% minus 95% gives us 5%. Or you can think of it as allowing your guesstimate to be wrong 1 in 20 times, which is the same thing. 100 divided by 5 gives you 20. Now, if we're assuming a 95% level of significance, then we want a p-value less than 0.05 to say our findings are statistically significant. This is what a p-value can do. It can be used to provide evidence against the null hypothesis of no effect. So if we have a low p-value, it means that the results we see in our test of nothing going on, since we always test the null, are rare, that low probability of occurrence. So when you're testing that null hypothesis, you want that p-value low so you can say you have significance. Here's some things a p-value cannot do. Although a p-value can give an indication of how rare a result would be given that null hypothesis of nothing happening here, it cannot be used the other way around to say that our alternative hypothesis is true. So if we reject the null, that doesn't necessarily make what we wanted to be true, what our research hypothesis, it doesn't make that true. It can be used to support your alternative hypothesis, but never to prove it. So you can say, yes, I rejected the null hypothesis, and that supports my alternative hypothesis, but you can't say it proves it. And then I put here in big bold, statistics never prove anything. Remember, they're just guesses. A p-value can't even be used to say the null hypothesis is true. There can be any number of things that are contributing to that probability, and a p-value alone is not enough. Also, statistics never prove anything, right? So always remember that. We don't give it too much credit. It just helps to inform you, but it does not make anything true or false or right. It just doesn't. It just gives a little support maybe of something that you kind of already assumed. Yeah, I was on the right track with that. Basically, that's what a p-value would do. Now, a p-value may show statistical significance, but this does not mean there is clinical significance. And I think we also covered that in the last webinar. The statistical significance would be that p-value less than 0.05 for your study, if you had that 95% level. But clinical significance, you might have something that shows significant, but it might be a very, very, very small difference, so it's not going to be clinically significant. And we're going to cover that a little bit more in just a few more slides. Here's some naughty things that researchers do with p-values. Some more things that you shouldn't be doing with them. Concluding that a significant p-value proves something, right? Changing the level of significance to accommodate an almost significant p-value. An example, and I've had this requested of me, it does happen. A test returns a p-value, say, of 0.06, but we tested for the 95% level of significance, so we wanted it to be less than 0.05. So it returns this p-value 0.06, so the researcher changes the level of significance to 90%. Instead of 95%. And voila, instant significance, right? Because now our p-value just needs to be less than 0.10, and here it is. So you can't do that. Don't change your level of significance after the fact. Another thing is what we call a fishing expedition. And that's when you take some data and you run lots and lots and lots of tests and you see what comes up significant. We call that inflating the type 1 error. And type 1 error is whenever you are falsely rejecting a null hypothesis. Maybe it should be the other way around. You're seeing significance that's not really there. And that's because you just tested it so much that it's bound to happen, because remember, we're allowing for a 5% chance of maybe making the wrong guess, or coming to the wrong conclusion. So you take lots of tests, you just keep upping that chance of being incorrect. I always like to say that if you look for a needle in the haystack long enough, you're going to find it. So, but maybe that needle shouldn't be found. It's a tiny needle in a haystack. It's really not important, so don't make it important. Going along with the fishing expedition is cherry picking. So here's somebody picked this cherry. It's that they're in love this one. I love this result, right? These are all our different results. So after I go fishing, then I work the hypothesis and study to match the findings I like. Maybe all these were all our ones that didn't quite make the grade, but here's the one part of the study that showed a really good p-value, or the one test for my fishing expedition, or maybe there's a couple of them that showed good, and I'm going to write about those and I'm going to present those, but I'm not going to talk about anything else. And so you shouldn't do that. If you have a study, you should complete the study and fully report your study. Don't cherry pick. Probably one of the biggest things with the p-values currently, and the reason that it's becoming more and more of an issue, is because of big data. There's more available data, many available computer softwares. It makes it a lot easier for not only researchers, but anyone really, to perform statistical tests. It's also garbage in, garbage out. So if you have a lot of untrained people doing this and coming up with some conclusions, and maybe they're working for a business, maybe for a sales department, and they're saying, well, we should focus our marketing here because this is what I'm showing. But if you're not doing it correctly, you could make a lot of bad decisions. And that's just one example. But p-values are practically useless with very large samples. One of the drawbacks of the frequentist methods is overpowering a study. And that is when you pull such a large sample that everything's going to look significant. It's so large that even the low p-values on everything, even the tiniest little effects, and I'm going to show you an example. But since the p-value is going to be significant for very large samples due to the overpowering, a researcher needs to look at some other measures. We can't just count on that p-value. One measure to use is the size of the observed effect. So it's not only is it significant, but how big of an effect was it? And that's where we have the effect size. Basically, how big is our effect? So according to Wikipedia, an effect size is a measure of the strength of a phenomenon. It tells us if the effect is significant. For the p-value, it tells us that, but an effect size tells us how big the effect is, what I just kind of said. There's many ways to compute a desired effect size, all kinds of hand computations you can do. It depends on the statistical test that you're planning, and depending on the test, we can see any number of effects, such as a mean difference. We would look for that effect in a t-test, or males and females different. Analysis of variance. Maybe there's 5 different school districts. Are they all different on some outcome? And that would be a mean difference. So that your effect would be the difference in the means, the difference in the averages. An effect size could also be a correlation. A correlation in itself is an effect size. That's the strength of association between two variables. And I'm going to show you some correlations in a bit. And a regression analysis also, you have effects for that, the coefficient. What's the effect on the outcome? And that's usually measured by your coefficient. And so there are many, many more depending on the test you're using. And as I said, we'll cover that more next month. Oh, we're already up to the examples. I was telling you about the big data and how it's a problem with the p-value. Here we have some results of a chi-square test. This is from a study years ago. There were 2 types of testing on HIV seropositivity rates, the percentage of people that were positive using a certain test. There were 2 different kinds of tests. There was one that was a rapid test and one that was just a regular test. This study had 480,697 people in it. That's how many records were in it. Very big. And here are our differences. Here's one before the test changed and one with the new test. So you had the 2 different test types that the people took. And the people were positive, HIV positive, 1.7% for the older test and 1.8% for the newer test. That's a difference of 0.1. Look at the p-value though, 0.004. That's significant at a 0.05 level. It's even significant at the 0.01 level. A very small p-value. But I really don't think a 0.1% difference is significant, not clinically. And so you kind of have to look at that. You say, well, yeah, my p-value is great. Don't just report that p-value and say you have significance and make your conclusions. You need to check the effect. You really should, especially in a case like this. So here is the hand computation you would use for the effect size. And it just happens that whenever I put in this chi-square statistic here, which is the 8.389, I divide it by the 480,697, and I take the square root of it, I come up with 0.004. It just happens to be the same as this p-value. That's just coincidental. Don't try to read anything into that. So we need to compute that, and it's a very small effect size. So here's how I would probably write it up. And in fact, this is probably how I did write it up. We talk about the results being significant. So here's our chi-square, here's our test statistic, here's our p-value. However, there was only a 0.1 difference in value between these two testing programs. With the seropositivity rate for the one testing program was 1.7, and for the other one it was 1.8. But then we did Kramer's V. It was computed for the effect size of the test, and it returned a very small value. And then I report that, and indicating a minimal strength of the relationship in the difference between these two percentages. So therefore, although the null hypothesis of no difference in proportions between those two testing types was rejected, the difference was too minimal to be considered clinically significant. So you kind of want to discuss that. Here's another example. This one is the correlations. And remember I said a correlation in itself is an effect size. Because a correlation, it goes between -1 and 1. 0 is right in the middle, means there's no real association that you can tell between the two variables. It's always between two variables. And of course, if they go negative, the closer they go to -1, the more they're moving in different directions. And the closer they go to a +1, the more they're moving similarly. Either both the variables are increasing together or both the variables are decreasing together. So it is, that correlation is going to tell you the size of the relationship, like the magnitude, and also the direction. Are they moving the same way or are they moving different ways? Here's a matrix of some correlations. We have 5 different variables. I'm not sure if you know how to read the correlation table, but it's like a matrix. So here I have, these are the different student activities. Okay, are they in sports? Maybe the students in the performing arts, maybe the student volunteers. And then we want to kind of correlate that with peer influence. Is peer pressure on alcohol associated? Is there something to do with being in sports and maybe having the peer pressure of drinking alcohol or in any of these other things? And then also a direct peer influence for marijuana. So we look over at these. When they're a correlation of 1, that means they're exactly the same, which makes sense. Here's student activity sports. Obviously, it's correlated with the same variables, correlated with itself. But let's look down at some of these other ones here. Here's somebody that's in, say, of students in performing arts. And then for alcohol. So we go and look at the direct peer influence of alcohol. And it's negative 0.079. It's a very small effect because according to Cohen, if we look down here, a correlation of 0.10 to 0.29 is weak, 0.3 to 0.49 is moderate, and 0.5 to 1 is strong. And that's either plus or minus. So it could be negative 0.10 to negative 0.29. It goes both ways, but it's just of absolute value here, 0.10 to 0.29. So Cohen doesn't even really care if the correlation is less than 0.1 because it's so darn close to 0, there's really nothing you can say about the two variables relationship. You can't tell anything about one variable by knowing the values of the others. They're not associated. So they really shouldn't be significant if they're less than 0.1 because there's nothing going on there. But if you look at this one, say we're looking at the sports, and then we want to see, well, let's look over here for marijuana. Okay, so a person's in sports, and these are teenagers, so the teenagers in sports, and then as the direct peer influence, like say the more peers or friends he has that smoke marijuana, you know, you would think, okay, is it going to go up or down, or is it going to have an effect? Well, it really shouldn't because it's 0.03. However, it's significant. See, here's our p-value right here. It's less than 0.05, it's less than 0.01, right? It's low, but it's significant. right? So it shouldn't be that way. I mean, it is, but the reason is because we have 11,000 records. So again, the sample size is overpowering this. So what we want to do is we want to take this into consideration. Yes, this is significant, but my gosh, it really isn't any kind of meaning at all. It's not even really a correlation. You know, it's not a strong, it's not even a weak effect. But let's look down at this one. This makes more sense. If you have a lot of peers that are drinking alcohol, and a lot of peers, they're associating with having a lot of peers that are smoking marijuana. So, you know, they're just absolutely doing both. We have a very strong correlation here, 0.695, and it's also moving similarly because they're positive. So the more friends you have that smoke alcohol, the more you probably have that smoke alcohol. They drink alcohol. The more you have that are drinking alcohol, the more you have that are smoking marijuana, right? It's just your peer group. So that you would expect, and that is also significant, but it's just as significant as this one up here. This one I would like to see be significant because it's strong. This one I don't want like that, you know. So you have to be careful with these p-values. They tell you some things, but especially with this big data, just falls apart. So we would want to mention this in our reporting, like we did with the chi-square test, with the seropositivity. We want to make sure that we're not going, oh, there was a significant association between being in sports and smoking marijuana, and it was negative. So people in sports were less likely to have peers that smoked marijuana, but it was very weak. So you need to make sure you say that. Don't just quote that p-value and get all excited. I think I've beaten this horse enough, right? So there are some other approaches to examining data, not just the effect size is always important. I think the effect size is very important, but there's also ways you can test data and you don't even use a p-value. You just totally eliminate that whole approach. I'm not going to really cover these today, but like I said, Google's our friend, so look them up. You can use confidence intervals or prediction intervals. You make a guess, you make your estimate of, say, a mean difference, and then you want to build your interval around it. Maybe the mean difference is 2 points, but it could be anywhere from -2 to 5. Well, right there, I would know that that wouldn't be significant because a zero's in there, right? And you would use that with the confidence intervals and a prediction interval. There's Bayesian methods, which I kind of briefly talked about a little bit ago, and you're assuming something already going in. With Bayesian methods, you're allowed to go, I know from past experience, or I know from previous studies, or, you know, I just know in my own head. Usually you have to substantiate it. I wouldn't just say, I just think, because then we're back to the frequentist I think. But you can use some information. You go in with a priori information. You might already know a certain difference is going to exist, and you take that into account. Likelihood ratios, these are great for diagnostic tests. So maybe you're doing a test to see if a person has cancer. A likelihood ratio will help you adjust those results because you also, again, go in there knowing what is the likelihood of a person in the population meeting these certain criteria. What's the likelihood they might might have cancer, and you take that into consideration. You don't go in blind. So those are good to have too. And there are many more. There's ones I was reading through and doing some more research for today. There were things I haven't even heard of. So Google's my friend too. So look some of those things up. There's a lot of current things going on. In fact, the American Statistical Association, it's unprecedented really, they issued a policy statement, and they usually, I don't think they've ever done that for actually how to do statistics. They don't really do that. They maybe give opinions and such, but an actual policy statement was actually published in March of this year on p-values and statistical significance, and here's the link to that. And these are free to download. All of these links, you can just go and get them. Very interesting reading, and in this article at the end, it also gives you many more references that you can look up. There's a journal actually that will not take any submissions anymore with p-values, and I think they said that as of last year, and that's the Basic and Applied Social Psychology. They won't. They don't even want to see t-value. They don't even see test statistics. They don't want to see an F. They don't want to see a T. They don't want to see a P. They don't want to see any of those letters. They like effect sizes. Actually, they say you can submit it, but they'll make you take out all the p-values before they publish it. There's also many more journals and dissertation committees that are asking not only for the p-values, but the effect sizes, and even the study power to be reported in submissions, which I think is really good. I really, in my opinion, if you're going to report a test statistic and a p-value, you really should be reporting that effect size, because p-values just tell you whether or not you reach significance on some criteria that you set for your study, but it really doesn't tell you how significant. It's just, is it or not? So the effect size gives you kind of an idea of the strength of your difference or your correlation, things like that. So we're going to discuss effect size and power more next month, and you can sign up down here. Here's a link for that, and they're free. And here's some more references. Regina Nuzzo, I think is how you pronounce her name, in Nature. Big thing going around. I see this posted all over the place, and it has been for a while. Very easy read. You don't have to be a statistician to understand it. In fact, the ASA guidance, the policy statement, is also a very easy read. This is a good one here, Greenland et al. They cover just about every misconception there is about p-values, and I think they have a cute little name for it, like a handbook of how to misuse p-values or something like that, so it's very good. And then, of course, here's the ASA statement again. Well, here's some offerings from Stats for the Masses and Omega Statistics. If you like this webinar, I would love you to come and see some more. We have some things going on here too at the office. We have our GoToMeeting conferencing software now, which is great. We can share our screens like I'm doing today. I can even record the sessions. So, our clients get to view them later. They really love these recordings when we go over results and such. It's very nice. We have revamped our website. I've been trying to do that for months and months and months, and finally it's up. Go visit it. It's very nice. Not all the way I would like it yet, but I'm starting to write blog posts. I'm trying to put together some tip sheets, white papers, things like that, so I can offer some more information to people. We're also putting together a survey database, and which would be great. I say it's great for researchers to use when you're searching for that elusive measurement tool. And there are a lot of free surveys out there. I always suggest don't design one. See if you can find one that's been tried and true. Designing a survey is a study in itself. If you want to and you really feel you need to, go for it. But if it's something where it's like, oh, I'm just doing this because I can't find something, look around for a survey. Usually there's something, or at least you can adapt one. But this will be useful, I think, having that database. Our last Back to Basics webinar is next month, and that's the power analysis one. And then we're going to take August off because we'll be on vacation. Not the whole month of August, but some of it, and I'm just not going to present in August. But September, we're going to be back with some more webinars. I want to do them every month. The third Wednesday of the month seems like a great time. So if you have any suggestions, I'm open. Send me an email. Let me know what you're interested in. I'd be glad to put something together because it is about you. It's about our audience, our people that come to watch these things. So I want to present something that you want to know about. So it's question and answer time. I'm going to bring on Rod, and he's hopefully found us some interesting questions. Hi, Rod, are you there?
I am here.
Great. Do we have any questions?
Is a test significant when the p-value is equal to 0.05 or less than 0.05?
That's a good question. Actually, that's another kind of controversy. Really, it's less than. We want it to be less than 0.05, or if you set it to 99% level of significance, we want it to be less than 0.01. If you set it at the 90% level of significance, we want it less than 0.1. We want it less than. We don't want it equal to. However, you will see some people that say, no, equals fine. Really, though, it should be less than. And that's just, it's also more conservative. I always say err on being conservative, especially if you're working with these larger samples and such. It's less than, okay? And, I can show you some journal articles or some work out there that shows it equal and some that show it less than, but I say less than. It should be less than.
How big is too big for a sample?
Another good question. I remember as an undergrad asking that, and everybody asks that. And I still don't have the right answer. There's no right answer because it depends. Statisticians love to say it depends. It depends. It depends on what you're studying. It depends on the test you're using. It depends on what levels you are setting. It depends on what size of effect you want to see. So we'll cover that a little bit more next month with the sample size. However, in many cases, anything over 50 is considered large. There are a lot of tests, especially the assumption check tests, like a Levine's test or a Kolmogorov-Smirnov test to see if we have normality, things like that. A sample size over 50, you're always, again, that p-value is always going to show significant. Even if you're doing this test, the KS test, that Kolmogorov-Smirnov test, and you're testing to see if your distribution is normal, you have 500 records. And you're looking at that histogram, and it's a beautiful bell shape, just beautiful. It looks perfect. But the test says it's not, because your p-value is low, right? The p-value say no, it's not normal. It's because that effect size is too small. That test is too conservative. So if you're doing a structural equation model, though, you want at least 350 records to be happy. So it really depends on what you're doing. I can tell you any sample size that's 10,000 records, that's large, you know, and with the big data, we're talking millions of records. I would say probably anything, depending on the test, but mostly anything over 500 records. That's just for about any test, and you have large. But it really depends on what you're doing.
One other question. This is from Jesse. The effect calculation for chi-squared is easy. Are they all that easy?
No.
And some effect size indicators such as Cohen's d, they have an attached p-value. Would that p-value prevent a low p-value due to overpowering a study?
Cohen's d is actually an effect size. I don't know if it has a p-value attached to it, so I'm not sure if I understand that part. But no, the calculations are definitely not always that easy. There's actually a software called G-Power. I'll pop it up on the screen real quick. It's free, so you can download the software. It's called G-Power. And this is to check your power, but you can put your effect size in. So say I want to do a t-test. Say I want to look at just a difference between two independent means, just a simple independent t-test. And I want to check and see how big of a sample size I need. So I'm going to do this a priori. I'm going to do a two-tailed test. Here's the effect size. Here's your Cohen's d. And here's all your different effects. You can have a small effect, a medium effect, and a large effect. Now you can use Cohen's d or you can use literature. It's always better to look and see what's already been kind of written about your study a little bit, you know, when you do your lit review, and see what kind of effects they were testing for. And you would want to use them. These are not the only three that you can use. I could say I want something between a small and a medium. Say I want a 0.3. I can put a 0.3 in there. So usually, as a statistician, our researchers tell us what kind of effect they're looking for. They kind of know that either from their literature or from their practice. They kind of have an idea. And so I will ask them. Sometimes they don't know, and I tell them, well, you need to figure that out because it's important. We need to know how big of a sample we need to test for this effect. So I'm going to throw that in. Here's my error probability. I'm allowing the 0.05 for my p-value. And then I'm going to say my power, you don't want it that powered. I'm going to say I'm going to go 80% power. And I'm going to have equal sample sizes. And I just calculate it. Boom, there's my sample size. So your effect size can be, depending on the test you're using, this is Cohen's d, it can be just about anything, but there's different ways of computing it. These ones come in. If you're not sure, you can click on determine, and it asks you to put in some information here, and it'll compute it for you. So G-Power is very nice if you want to get that and play with it. But I'm not sure about the p-values associated with an effect size. That I'm not sure.
Elizabeth asks, how to calculate, measure the size effect of an interaction effect?
That's a good question. That's a little more complicated. It would depend on the study. I'd have to see the study, and I'd have to see what the variables are that we're looking for the interaction effect. But it's basically, it would be put into the study as a variable. Usually if it's a regression, an interaction, you're just multiplying two variables, and that would be your term. That would be your variable, would be that multiplied interaction. And then you would just get an effect on that. But it would depend on the study and what kind of test you're putting that interaction in. But certainly it can be checked. But it would depend on the context. Again, it depends. If I saw the information, and so, yeah, definitely we could do it. It can be done. Absolutely. An interaction, like in a regression, is just another variable. So it would be calculated kind of similarly as just a variable. An interaction in an ANOVA or something might be calculated a little bit differently.
Another question just popped in from Elizabeth. So you meant just by seeing the coefficient?
Well, the coefficient could be an effect. Usually it's the standardized one. It's your beta, not necessarily your raw coefficient. It would be that beta coefficient would be a good indicator of effect.
What if my sample size is very small? Is the p-value more useful then?
More useful? Probably not, because if your sample size is too small, even if you have really, really good large effects, you're not going to get a good p-value. You're going to get, because now your study's underpowered. So power is a big deal. You want to make sure that you have enough of a sample to meet the criteria of your study to be able to see significance in the effect that you're looking for. So it's important to know what effect size you're kind of looking for up front. But if your sample size is too small, and say you have a mean difference, and you can see there's a big difference there, you will get a p-value probably that's not significant if your sample size is too small because you're underpowered. And then you're going to be saying there's no difference. But again, you're going to take that into consideration and you're going to write it up in your results that, oh yes, like for instance on a t-test, the males and females had a mean difference of 50 points, on a 100-point test. Well, that's definitely means something, right? There's a difference there. But my sample size was too small, so the p-value was like 0.12 or something like that. So, you're going to conclude your hypothesis test that yes, we failed to reject it, but you're also going to put a caveat in there. The power was too small. And you're probably going to want to report your power, which is another calculation, or a lot of times your software will return the power number if you ask for it. But I guarantee then you're going to be underpowered. And it doesn't make your p-value more important. In fact, it makes it kind of not as important. P-values, I guess that's another argument for saying p-values, while they're good and people use them, you can't make all your conclusions on them.
Jerry asks, what if one group has a small size and the other group has a large size? How will this affect the p-value when you're comparing them?
Again, it depends on the test that you're using. A lot of tests, you don't need to have the equal sample sizes. Very rarely. I mean, in textbooks, you'll get the equal sample sizes, but in real life, you don't. There are adjustments you can do to sums of squares, things like that in an ANOVA and in some other models. You just look at some different outputs. I think greenhouse geysers, another statistic you can look at when they're unequal. I use SPSS quite a bit, and these are statistics that come in your output when you're running these tests. And they just do the computations a little different. So you would use the p-value associated with the test that best suits your differences there. So if you have a test that's sensitive to different levels of sample sizes, different group sizes, then you should use the appropriate test statistic with that adjusted p-value. But yes, it does. It does have an effect.
That is it for the questions.
That's it. Wow, we had a lot of questions today. That's great. Well, I thank you everybody for coming. It was very nice to have everybody here, and it's a lovely afternoon, and I hope you guys sign up for next month. Sometimes I feel like I don't share enough, but we only get an hour, so usually it's just I'm going to throw some things at you, and then you go out there and think about it some more. But if you have any other questions, definitely email me. I'm going to get this put together. You'll have your slides and your recording in the next couple days, and I look forward to seeing everybody next month, and thank you again. Okay, bye.